Hey guys, in this video we're going to talk about 7.4 algebraic identities and trig substitution, specifically trig substitution. So how can we use trig identities that we've learned before in trigonometry to simplify and evaluate integrals? Okay, so the main identity that we're going to be using is called the Pythagorean identity. Probably learned it in trig. Cosine squared of an angle plus sine squared of another angle equals 1. So our first example, we are trying to integrate 1 over the square root of 1 minus x squared dx using the substitution x equals sine theta. And the reason we can make this substitution is because sine of theta can be between -1 and 1. And the domain of this function, the only restriction here is that, it has to be bigger than 0 because we can't have 0 in the denominator. So we end up getting x squared is less than 1. If we take the square root, we get that x is between -1 and 1. So that's why this substitution is valid, because of those domains and ranges. So that was just a side note. Let's go ahead and get into it. So it tells us to substitute in x equals sine of theta. And we're going to assume that theta is between -pi/2 and pi/2. So here's -pi/2, here's +pi/2. So theta is going to lie in one of those quadrants, either quadrant 4 or quadrant 1. So let's make the substitution. So we have 1 over the square root of 1 minus sine theta squared. Now, since we're integrating with respect to theta now, we want to make sure that we take the derivative of both sides of this guy to give us that dx is equal to derivative of sine is cosine d theta. So I'm going to sub in, instead of dx, I'm going to sub in cosine theta d theta. Alright, now what you should recognize here is the Pythagorean identity. So again, we have cosine squared plus sine squared equals 1. And I can make this equation look like the one under the radical by subtracting sine squared from both sides. When I do that, I get cosine squared is equal to 1 minus sine squared. So I'll make that substitution. And I'm also going to write the cosine theta on top, right here. Now, because theta is between -pi/2 and pi/2, cosine is positive in these two quadrants. Remember, cosine is the x value. Since that's the case, when we take the square root of cosine squared, we're just going to get cosine. And of course, something divided by itself is just 1. So this is just equal to 1 d theta. And of course, we know that the integral of 1 d theta is just theta. Now I want to make sure I'm back in terms of x. Theta plus c. So what I want to go do is I want to go back to where I made my original substitution, right here. So I have theta, and to get theta in terms of x, I have to take the inverse sine function of both sides to cancel out that sine. So let's do that. Whatever I do to one side, I have to do the other. So that cancels out, and I'm just left with theta is equal to sine inverse of x. So there we have it. This is sine inverse of x plus c, of course, because it's the indefinite integral. And that's it. Let's do another example. So here's a little tidbit. This is a hint for your homework when you're doing these problems. So if you have a form like square root of a squared minus x squared for a constant a, try this substitution. That's what we did here. Because here our a was equal to 1. 1 squared is 1. So we had a squared minus x squared, so we made that substitution. So let's see if we can do that again. Okay, well, let's see what I have here. So we do have the form a squared minus x squared. In this case, and maybe to see that easier, I can write 4 as 2 squared. And then I can just apply this substitution since I'm in this form. A is 2, so my substitution is going to be x is equal to 2 sine theta. Therefore, dot, 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 that's what I do for therefore. Therefore, dx, if I take the derivative of both sides, dx is equal to 2 cosine theta. And now I can make my substitutions. So, carrying everything over here. So 2 squared, I'll just leave that as 4. X is 2 sine theta, so this is minus, putting it in for x right there. 2 sine theta squared. And now that I'm in terms of theta, I want to make sure I sub this dx in for 2 cosine theta. Oh darn, I forgot my d theta. That's not cool. Alright, there we go. So this is where I'm at. I'm good so far. Now I want to, the idea here is to either end up with a cosine squared or a sine squared in the denominator. So let's mess around with the denominator a little bit. The numerator, I'm just going to carry this 2 cosine up there. And the denominator, if I do 2 sine theta squared, I just get 4 sine squared theta. And I'm starting to get into a good place because notice on the bottom, when I factor out a 4, I get that Pythagorean identity that I like. So let's go ahead and do that. Let's factor out a 4 on the bottom. Under the radical, so I'm left with 1 minus sine squared when I factor out that 4. And now I have the magic identity. 1 minus sine squared is equal to cosine squared. So this is 2 cosine over the square root of 4 cosine squared d theta. Again, since theta is between negative pi over 2 and pi over 2, cosine's always going to be positive. So when we take the square root of cosine squared, it's just going to be cosine. So this becomes 2 cosine on top. Square root of 4 is 2. Square root of cosine squared, as we said, was cosine. And now what's cool about this is this all cancels out to 1. So we're left with 1 d theta. And this is going to give us, of course, theta plus c. Now we want to make sure that this theta is in terms of x, or original variable. So we go back up to our substitution. we saw that we had x equals 2 sine of theta, so let's write that down here. X equals 2 sine theta. So we want to isolate theta by first dividing both sides by 2 to give me sine theta. Maybe I'll keep it in yellow. It's going to give me sine theta equals x over 2. And I need to undo sine by doing the sine inverse of both sides. So that's going to give me, I'm going to do it down here. Since sine inverse and sine are inverse operators, they essentially cancel each other out. And I'm left with sine inverse of x over 2 is equal to theta. So there it is. Let's go and sub that back in. So instead of theta, I'm writing sine inverse of x over 2 plus c. And this is my final answer. Find the area of the ellipse 4x squared plus y squared equals 9. So this is a pretty cool problem. So we have some kind of ellipse on the plane. So remember, an ellipse is kind of like an oval shape. So it looks like something like this, maybe. And what we're going to do is we're going to use integrals to figure out what the area of this thing is. Pretty neat. The first thing I'm going to do is I'm going to take this equation and I'm going to isolate y so that I can put it in Desmos. So the first thing I can do is I can subtract 4x squared from both sides. So give me this guy. And then what I'm going to do is I'm going to take the square root of both sides to isolate y. Now typically you would have plus or minus, but since we're putting this in Desmos, I don't know a way to do plus or minus. We can just use the positive version to see what that corresponds to. The positive version of the square root is going to correspond to basically the top half of this ellipse. And the negative version is going to correspond to this bottom piece, basically. So let's see what this looks like in Desmos. Okay, so there it is. So the idea here is that we're going to integrate this guy and then multiply by 2 to find the area of not only the top but the bottom. So here we're starting at negative 1.5 or negative 3 over 2 to 1.5. So what am I integrating here to find that area? Well, let's set it up. So I'm going from negative 3 over 2 to positive 3 over 2. And my function is, so again, we're just integrating the top half, and then later on we'll multiply by 2 to get the orange part. So now I have this guy. So what we should recognize is that we have a radical of the form a squared minus x squared, right? And here a is going to be 3, right? Because we have 9. And actually, maybe I'll just write this, just so we have every single step written out. Let's write this. Okay, so we have 3 squared minus, and then we have 2x squared is the same thing as 4x squared. That way, you know, I can see what I have to substitute here. So the substitution that I'm going to make is, instead of, you know, letting x equal a sine of theta, in this case, our x is actually 2x. So we have 2x equals 3 sine of theta. This is going to be our substitution. I'll do it in purple. I'm going to just kind of erase all this other stuff. So far, what did we do? We set up an integral to only integrate the top half of this ellipse. Once we figure out that area, we'll just multiply it by 2 to get the area of the entire ellipse. So we recognize that we have an a squared minus x squared kind of form, and so we can use a substitution. The substitution we used was 2x equals 3 sine of theta. All right. From here, I can take the derivative of both sides to give me that 2 dx is equal to 3 cosine theta, and therefore dx is equal to 3 over 2 cosine theta, dividing both sides by 2. Now, remember from last semester, if we are punching in, d thetas, I forgot this d theta, if we're integrating with respect to theta, our limits of integration have to change, because originally I was going from negative 3 over 2 to 3 over 2 with respect to the x-axis. But I want to see what these limits are with respect to theta. So I need to find the new limits of integration. And we're going to use this guy to do it. So originally we had x is equal to negative 3 over 2 as our lower one. So instead, if I plug in negative 3 over 2 in for x, I get an equation for my new limit, my new lower limit. So simplifying that out, I get negative 3 equals, maybe I'll just keep doing it in purple. Then if I divide both sides by 3, I get sine of theta equals negative 1. And so because we're assuming, if we take the inverse sine function of both sides, inverse sine is defined between negative pi over 2. Let me write this. This you might recall from trig, but if you don't, I would write this down in your notes. So recall that sine inverse of x is between negative pi over 2 and pi over 2. So if I take the inverse of both sides, those cancel, and I'm just left with theta. Well, what angle has a sine value of negative 1 in this interval? That's going to be negative pi over 2. So originally, my lower limit was negative 3 over 2, but now it's pi over 2, or negative pi over 2, since it's in terms of theta. So let's replace that here. And we can do a similar process with 3 over 2. I mean, it's kind of the same idea here. If we plug in 3 over 2 into my substitution formula, I just get 3 sine theta equals 3, so sine theta equals 1. Taking the inverse, I get theta is equal to sine inverse of 1, and that has to be pi over 2 in this interval. All right, so that's my upper limit. Now we are in a good spot, you guys. All right, so we took care of the limits with theta. Now we have to replace dx in terms of theta. We want everything to be theta, 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 theta. So instead of dx, we can write this guy. Let's do it. So we have negative pi over 2 to pi over 2, and then we have this business. And actually, I'll just make the substitution in here. We said that 2x was equal to 3 sine of theta, so that's what I'm going to put right in here. 3 sine theta. These problems are so fun to me, I don't know why. And instead of dx, we're multiplying by 3 over 2 cosine theta d theta. Didn't forget that time. All right, guys, now we are in a good position here. So now under the radical, you may see something that looks good. When I square 3 sine theta, this becomes 9 minus 9 sine squared theta. And I'm going to bring out the 3 over 2 just because it's annoying me. This one right here, I'm bringing it out to the front. Times cosine theta d theta. Okay? And now you might be having an epiphany. I hope so. And you can say, oh, well, look under the radical. Look what I can factor out. I can factor out a 9. And then I'm just left with 1 minus sine squared. Then I still have that cosine that's being multiplied on the outside. Well, 1 minus sine squared is the same thing as cosine squared by the Pythagorean identity. So that's getting replaced. We're always trying to condense this. It's starting to look a little prettier now, guys. All right, so let's take the square root. Square of 9 cosine squared, we just get 3 cosine theta. We still have that cosine theta d theta. Now I'm also going to bring this 3 on the outside right here. When I multiply that in the front, I just get 9 over 2. So let's do that. Make it look a little cleaner. Oh, it's not going to let me go down anymore. Wow. That stinks. Okay. Well, actually, let's just let's just make room. Okay. All right. So I'm going to just rewrite it at the top so we have some more room to work. I need to maybe start writing a little bit smaller. Okay, there we go. So from here, I can use that table of integrations found in the back of your book, or, you know, it's that document that I stuck in last week's homework. This is going to be for number 18. And what that tells us, and I'll just write it out here, is cosine n of x dx is equal, maybe we'll just use theta. How about that? Cosine n of theta d theta is equal to 1 over n cosine of n minus 1 theta sine of theta plus n minus 1 over n cosine n minus 2 theta d theta. So this is the rule we're using, and I chose to use that rule because this is like my n. You know, I have cosine of 2, like I have the integral evaluated right here. So that's what I'm going to do. N is equal to 2, and I'm just going to use that formula. So let's do it. So cosine squared, well, I have 1 over n. In this case, n is 2, so 1 over 2 cosine to the 2 minus 1 theta sine theta plus 2 minus 1 over 2 cosine of 2 minus 2 theta. And I'm evaluating from negative pi over 2 to pi over 2. So it's a definite integral. All right, so let's clean this thing up a little bit. Clean up the exponents in particular. There I am running out of room again. Anything to the 0 power is just 1. So I'm going to just rewrite this as 1 d theta. All right, so let's go ahead and evaluate the mini integral in there. I'm just writing it step by step so you guys see what I'm doing. So this guy is going to turn into theta. So this becomes 1/2 theta, and we're evaluating this whole thing from negative pi over 2 to pi over 2. Ran out of room again. Okay. I wish they would make this thing scroll forever. Could just keep doing math forever and ever. Okay, so let's see what happens next. Alright, so we have this 9 over 2 on the outside. Now I'm going to start evaluating at my limits. So I'm going to first plug in pi over 2 anywhere I see a theta. Remember how we did this? So we're doing cosine pi over 2 times sine of pi over 2 plus 1/2 pi times pi over 2, right? So we took this upper limit, and then we're subtracting by the lower limit when I plug in negative pi over 2. So I have 1/2 times cosine of negative pi over 2. And a lot of things are going to cancel. It's not going to keep getting uglier, I promise. All right, so that's a wrap for that. Okay. This problem is crazy. So what's cool is that cosine pi over 2 is 0, so all of this gets slashed because it's all stuck together by multiplication. So right here we have a pi over 4 that we can just put down there. Minus, all right, we got some other things that are getting slashed. Cosine of negative pi over 2 slashes to 0. That's stuck together with multiplication. And then this guy right here becomes negative pi over 4. So we have basically this, right? Double negatives make a positive. Let me look at my notes and make sure that we are not going down a rabbit hole. Yeah, this looks good. So this becomes 9 over 2, 2 pi over 4. Multiply it out. We get 18 pi over 8, or simply if we divide top and bottom by 2, 9 pi over 4. So what is this again? I know it's been a while, but what this is, what we just found, is we found the area of the top part of the ellipse. Now to find the area of the, to find the total area, which is what the problem originally wanted, we have to multiply what we got here, which you can see in the picture, by 2. So total area is 9 pi over 4 times 2, which is 18 pi over 4, which is 9 pi over 2. So this is the total area. This is our final answer for that ellipse. That includes the top and the bottom portion. Very cool. Thanks for watching. I'll see you guys in the next problem. So we can also make tangent substitutions. So integrals involving a squared plus x squared may be simplified by a substitution involving tangent and using the trig identity tangent theta equals sine over cosine. So let's get into an example, and I want to also show you something really cool. You know, these identities don't really come out of nowhere. We can actually use triangles to derive these helpful identities. So the first thing I'm going to do is I'm going to just do an example here where we're given the substitution, you know, directly. It's telling us to sub in x equals 3 tan theta, and then I want to show you why that substitution was chosen. All right, so let's go ahead and just do the substitution first. They're telling us to plug in 3 tan theta in for x, so let's do that. And so remember, we want these variables to match, so we need to go ahead and take the derivative of both sides of this guy. The derivative tan is secant squared theta. It's just one of those special trig derivatives. So this is just going to be 3 secant squared theta. And we can go ahead and replace dx with that. All right, good. So we got our d theta in there. Everything looks peachy. So let's go ahead and clean this up a little bit. I'm just going to put the 3 secant squared on top just to make it look a little bit nicer. And then on bottom, well, 3 tan theta squared is the same thing as 9 tan squared theta when I square that thing. And at this point, you should recognize that, hey, we can take out a 9 here on the bottom. And it's looking like a Pythagorean identity, right? If we take out that 9, we get tan squared plus 1. It's always good when you see a 1 and something squared, a trig function squared, because this kind of tells me, oh, we're pretty close to a Pythagorean identity here. And I'm going to just quickly derive what this identity is. So, you know, we know good old cosine squared plus sine squared equals 1. We know that. We love this identity. Oops. Sorry, guys. I don't know what happened there. That was a weird thing. All right, back to business. So I want to introduce a tangent squared into this formula. I want to somehow derive that. So I'm going to use the identity, this is from trig, that tangent of an angle is equal to sine of an angle over cosine. This is the quotient identity from trig. Quotient identity. And because I know that, what I'm going to do to both sides of this equation to introduce a tan squared is I'm going to divide everybody by cosine squared. I can do that. Whatever I do to one side, I can do to the other. And the reason that I did that was because I recognized here, hey, that's tan squared, right? Because of the quotient identity. So cosine squared over cosine squared is 1. This guy, as I just said, is tan squared from that quotient identity. And 1 over cosine squared is going to be secant squared. And, you know, I would review, if I were you, my trig identities if this isn't ringing a bell. This is a reciprocal identity, that 1 over cosine squared equals secant squared. So, you know what's cool is, look at this. This is equal to this, right? So since 1 plus tan squared equals secant squared, we can just go ahead and chuck it in there. And I'm chucking it because, look, on top I have a secant squared. So we're getting closer and closer to something nice. Let me make sure. All right, I just want to make sure my mic was plugged in. Yes, I do have a mic. I am basically doing a math podcast in my office. So here we go. 9 secant squared, that's being replaced. All right, check this out, guys. Look at that. Those divide out. 3 over 9, I'm pulling out, and 3 over 9 is actually just 1 over 3. So check this out. So cool. So, of course, the antiderivative of 1d theta is just theta. So this is 1/3 theta. And we want to make sure we go back to our original variable, which was x. So I'm gonna do this 2 ways. All right. So we know that x is equal to 3 tan theta right here. So I'm gonna just pull this down here. So x is equal to 3 tan theta, and I want to isolate theta. So if I divide by 3. If I divide by 3 on both sides, I get tan theta is equal to x over 3. Take the inverse tan of both sides. And we get that theta is equal to tan inverse of x over 3. So that's what we're going to put in there. So this is my answer. All right. Now I want to show you where in the world we are getting these substitutions from. All right. And it has to do with a triangle, how we draw a triangle. So so this was the answer. I just want to kind of circle back to the beginning. You know, where are these freaking substitutions coming from? Like, how weird. Why are we substituting in x equals tan or 3 tan theta? Why would we do that? Oops. Keep doing that, man. Let's see. So it all has to do with a triangle. A right triangle in particular. In trig, we used right triangles to figure out trig ratios, and you probably did that in geometry too. And if you look at the bottom of this, doesn't this look very suspiciously like the Pythagorean theorem? A squared plus b squared equals c squared. Well, in this case, we can identify the legs. We can say that, you know, this looks suspiciously like x squared plus 3 squared, which we have. So if we kind of like convert this to a right triangle, this information. So here's my angle theta, whatever. And we know that one leg is going to be x and the other leg is going to be 3, just based on what we were given. So if this is x and this is 3, well, what does the hypotenuse have to be? Well, if we solve for the hypotenuse, if we square both sides, the hypotenuse had better be square root of x squared plus 3 squared, right? Now, if I use the legs as they are, what I end up getting is tan theta equals opposite over adjacent. So I get, you know, if I try to isolate x, I get x tan theta when I multiply by x. And then if I divide, I get tan theta equals 3 over x. Or sorry, what am I doing? Just went back. I just did the same thing. So no, I actually get x equals 3 over tan theta, which is not that nice, right? Because this is going to end up being 3 cotan theta, which is kind of gross. I don't want to use cotan. So instead of that, I can just switch the legs around. Like, I don't have to call this leg 3 or this leg x. I can just switch them. I can actually call this leg x and this leg 3 to make this look a little bit nicer. And when I do that, you guys, I get tan of theta is equal to opposite x over adjacent 3. And so if I multiply both sides by 3, I get 3 tan theta equals x, and that is where my lovely substitution up here comes in handy. So, you know, we're just working with triangles here at the end of the day. And, you know, this was, remember we had that theta was equal to, so we had tan theta equals x over 3, and theta is equal to tan inverse of x over 3, which makes sense, right? Because, you know, the tangent of this triangle, opposite over adjacent, is x over 3, so the angle is going to be inverse tan of that ratio. So just a little connection there. And maybe we can draw triangles from here on out just so you guys can see the connection. Okay, so here's the little rule. To simplify a squared plus x squared or square root of a squared plus x squared for a constant a, try the substitution x equals a tan theta, with theta being between negative pi over 2 and pi over 2. And we don't have the little line under here because tangent of pi over 2 and tangent of negative pi over 2 is undefined. So we don't include those values there. All right, so let's do another example. Use a tangent substitution to show that the following integrals are equal. So what I'm going to do is I'm going to work this integral out, and hopefully at the end of the day I get this one. Then we're going to take a look on Desmos to see what these guys represent, what the areas represent. All right, so let's start with this good old integral, 0 to 1, 1 plus x squared, taking the square root of dx. All right, so I'm going to just draw a triangle just so you guys can see it, see what's happening here. So this looks like a hypotenuse, the square root of 1 plus x squared. And if that's the case, well, if this is theta, then this guy must be 1, this guy must be x, maybe. Let's adjust it if we need to. But remember, we're trying to use the substitution x equals a tan theta because we have a square root of a squared plus x squared. So here our a is clearly 1. So we want to make the substitution x equals tan theta. Does our triangle agree with this substitution? Well, in our triangle, the tangent of theta is opposite x over adjacent a, which is x over 1, which looks good. So this agrees, this picture agrees with the substitution that we're going to make. So x is equal to tan theta is the substitute. Ooh, maybe I'll draw it over here. Actually, let's do that. So our substitution is x equals 1 tan theta, or simply tan theta. Now I need to get rid of that thing. So if I differentiate each side, I get dx equals secant squared theta d theta. So let's go ahead and make my substitutions. And I also need to fix my limits of integration. All right. So let's first, let's fix the limits of integration as well. So this is one thing we need to fix. The other thing is we need to get those limits in terms of theta and not in terms of x. So we use our substitution here. Originally, our lower limit was x equals 0. So in for x, I'm putting 0 right here. 0 equals, tan theta, and then I just figure out what theta is. So if I take the inverse, tan inverse of 0 on both sides, I get theta isolated. So the question is, which angle between negative pi over 2 and pi over 2 has a tangent equal to 0? Remember, tan is y over x. So if we look at our unit circle, the only value that will correspond to this is theta equals 0, right? So this is coming from the unit circle. Y over x is equal to 0, because when theta equals 0, when theta, let's write it down here. When theta is 0, what we have is the coordinate, 0 radians is going to be x equals 1, y equals 0. So when we do y over x, we get 0 over 1 equals 0. All right, so the moral of the story is tangent of 0 is 0. So this is also going to be 0, but it's, 0 radians, not 0 in terms of x. All right, beautiful. Let's do the upper limit here. All right, so we have, instead of x equals 1, we want to figure out what that is in terms of theta. So plugging in 1 in for x, I get 1 is equal to tan theta, taking the inverse tan of both sides, well, of course, that cancels out, and I'm left with theta equals tan inverse of 1. So this is asking, where is tangent of 1 on the unit circle? Well, tangent of 1 happens when y equals x, because when we divide them out, if the numbers are the same, we get 1. And that happens at pi over 4. So tangent inverse of 1 is pi over 4. All right? Maybe if you do this in the calculator, it'll give you 45 degrees, but I like radians, so we're going to do pi over 4 right here. All right, so cool. We got our limits of integration changed. Instead of 0 to 1, we're going from 0 to pi over 4. Very nice. And instead of the dx, we're making this substitution in to be in terms of theta, d theta. So we got secant squared theta d theta in replacement of that. Let me clean some of this up because it's getting messy. And instead of x, we're making the substitution x equals tan theta. So let's do that right here. All right, so let's clean this up. So again, we're going from 0 to pi over 4. On the inside of the radical, if I just squared, this is just 1 plus tan squared theta times secant squared theta d theta. Now from the previous problem, we've derived that Pythagorean identity. I guess I erased it. But we know from the previous problem that 1 plus tan squared theta 1 plus tan squared theta is equal to secant squared theta. So that's what I'm going to sub in here because I see that secant squared just hanging out outside waiting for a friend, waiting for a fellow secant squared to intermingle with. So the jokes get worse as the day goes on. So 1 plus tan squared is just secant squared, so I'm doing that sub. And the square root of secant squared is simply secant. And if you want to get technical about it, you know, this square root, I mean, it has to be positive secant versus negative because of our interval. Cosine is always positive from negative pi over 2 to pi over 2. So we don't have to worry about positives and negatives here. It's just secant times secant squared theta. All right, cool. So let's see what this gives us. Well, I think we did our job because now we have secant cubed theta d theta, and by the reciprocal identity, this is just 1 over cosine cubed theta d theta. So we just proved that the integral that we started with, this guy, is equal to this guy. We proved that. Now, it doesn't tell us to evaluate the integral. If you wanted to, you totally could. I think you're going to have to use integration by parts here, though, if you want to figure that out. I'm not going to do all that, but what I do want to show you is what this is on Desmos. You know, remember, integrals are just, you know, when we find the integral of a function, when we're taking the definite integral in particular, we are looking at the area under a curve for some, you know, between two values. So let's check this out on Desmo. So let's do it. We have, let's see, 1 plus x squared square root from 0 to 1. Let's put this back on. So we're taking the 1 over the square root of 1 plus x squared, I believe, right? Was that it? No 1 over, just 1 plus x squared. Okay. 1 plus x squared. All right, so we get this guy. And so let's just put in, you know, these bounds, I guess. X equals 0 to x equals 1. All right. So, you know, if you look in between these lines, that's the shape that we're finding the area of, you know, when we take this integral. Now, if we put in the other one, which was 1 over cosine cubed, so we're going from, and I'm using x because, I'm using x instead of theta because that's what Desmos likes. So we're going from, let's see, cosine 1 over cosine, and I think it doesn't like cosine to the third, so I'm just going to put it in like this, cosine cosine. And we're going from x equals 0 again to x equals pi over 4. Okay, so this time we're looking under the black curve, and that area should be the same as the area from the green line to the purple line under the blue curve. All right, so this time we're just looking at the area under the black curve for cosine. And so those areas should be equal. The area of under the black curve from green to red versus the area under the blue curve from green to purple. Those should be the same areas, okay? So that's a little visual representation of what we just did. Let's go ahead and move on here. So in this example, we are going to employ a method used in algebra called completing the square to make a trig substitution. If we look at what's under the radical now, it's not in the form of x squared plus a squared, or an obvious form, or x squared minus a squared, etc., a squared minus x squared. So we kind of have to mess around with this to get this to look like how we want it to. And the trick is to complete the square. So let's remind ourselves how to do this. What I'm going to do is I'm going to take what's under the radical and I am going to turn this into something squared, plus or minus something, so that I can use a trig substitution. And so what we're trying to do is figure out how we can rewrite this to be in the form of x squared plus a squared. So how do we do it? Well, there's this little trick in algebra called completing the square. And basically what you do is, the first thing you do is you factor out a negative because we want the coefficient of x squared to be positive. So that's what I'm going to do first. I'm going to factor that negative out. And I left a big space here because the completing the square part happens, we take the number in front of x and divide it by 2. So first, take number in front of x and divide by 2. This is going to give us negative 2 divided by 2 is equal to negative 1. So this is our, I'm just going to call it the magic number for now. Okay, so that's my first step. And the second step is to square the number you got, square the number that you got in step 1. So the number that we got was negative 1. So we take negative 1 and square it to get positive 1. And that's what we're putting in here. Okay, so the equation is now not completely balanced because if you look at the left side and the right side, we just introduced not a positive 1, we actually secretly introduced a negative 1 because of this distribution. So we have to introduce a negative 1, excuse me, over here as well to keep it balanced. All right. Once we do that, we can now condense this using the magic number. So the magic number is going to let us condense this thing to x magic number squared. Okay, so that's how that completing the square algorithm works. Now, if you don't trust me, you should FOIL this back out and see that you get this guy. But anyway, now we're in a good position, okay? So what we want to do next is, remember, we're trying to sub 2x minus x squared, aka this. So we need to get it by itself and add that 1 to both sides. All right, so we have this equals negative x minus 1 squared plus 1. All right, and now I can make my substitution. That's what I just found is what I'm going to put in under there. So let's do that. So now we have 3 over radical negative x minus 1 squared plus 1. And I hope you guys can kind of see where this is going. Now we're in the form, you know, x squared plus a squared. So that tells us that we can use a trig substitution. So how are we going to do it? Well, here's what we can do. The first thing I'm going to do is I'm going to rewrite this so that the constant is in the front, so that it's square root of 1 minus x minus 1 squared dx. And so we can see now that this is our a squared, and this is acting like our x. And so in this case, since we have a squared minus x squared, we can use the sine substitution trick. So that tells us that whatever is acting like x, which in this case is x minus 1, is going to be equal to a, which is 1, sine of theta. We don't have to write the 1 there. Oh, there goes the battery. And so that is what I'm going to do. I'm going to go ahead and substitute x minus 1 with sine and hopefully clean this up a little bit. So here we go. Let's maybe do it over here. So I have 3 over 1 minus sine of theta squared, and now we need to get rid of this thing. So if I take the derivative of both sides, the derivative of x minus 1 is just 1. So 1 dx, derivative of sine is cosine theta d theta. So in replacement of the dx, I'm going to put cosine theta d theta. All right, looks good. Everything looks good. We don't have to mess with the bounds because it's an indefinite integral. All right, beautiful. So I'm going to pull out that 3. I don't like it. Let's pull it out. And then we have cosine on top over, well, this is just sine squared, 1 minus sine squared. I hope you guys see where this is going. So 1 minus sine squared by our Pythagorean identity is cosine squared. Replace that. And the square root of cosine squared is just cosine. Oh, I forgot my 3. There we go. So cosine over cosine d theta. So we end up just getting 3, 1 d theta, and here we just, of course, since we're integrating with respect to theta, the integral of 1 is just theta. So that's what we have. Now we want to sub in our original variable. We don't want theta here. So remember what our substitution was. X minus 1 equals sine theta. Let's write it here. And so I need to take the inverse of both sides to get theta, the sine inverse. So I get sine inverse of x minus 1 is equal to theta. So my final answer, you guys, is 3 times sine inverse of x minus 1 plus c. All right, let's do another example. So this time we have a trinomial again. We can't factor it. We want to be able to do a trig substitution in this case because, you know, if we were able to factor this, it might be easier to do a fraction decomposition, but we can't factor it, unfortunately. So let's mess around with this thing, complete the square, and do some substitutions. All right, so this is what I have, you know, my x squared and my x term. I want to go ahead and complete the square, but first I'm going to kind of write it like this. I'm just going to leave this off to the side and do the completing the square step on the right side and kind of balance it at the end. So complete the square, I take the number in front of x and square it, and I get +1. I believe. Or sorry, I missed a step. I missed something. We have to do, so step 1, maybe I should write the steps out myself. We take the number in front of x and divide it by 2, and then we square it to give me a 4th. And then, you know, I'm gonna shrink this down using the magic number that we found, which was 1/2. But I want to make sure that the left and the right side are balanced. And the only thing that is an issue here is this is +1 on the left. This is +1/4. So we need to like do 1 minus a 4th to get whatever else I need to add, which is 3/4. So the magic number was 1/2 when we divided b by 2. So that's what this thing's gonna, in orange, that's gonna shrink. This is gonna shrink to x plus 1/2 squared plus 3/4. All right, cool. So now I have this. This is all balanced. Beautiful, 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 beautiful. What I'm gonna do from here is I'm gonna sub this in here because now I'm in the form a squared plus x squared. Let's do it. All right, so we have 1 over, this is what I'm subbing in. I'm gonna write this in the front though, plus, maybe I'll just, how about I just do it in black? 3/4 plus x plus 1/2 squared dx. All right, guys, we are in a good position. We're in the form a squared plus x squared, right? And in this case, we need to figure out what a is. So we know, you know, this is 3/4 is equal to a squared. Therefore, if I take the square root of both sides, a is equal to the square root of 3 over the square root of 4, which is the square root of 3/2. Cool. So what's our substitution be? Well, this falls into tangent category, the tangent category. So what's acting like our x is this x plus 1/2. That's the other thing that's being squared. That's not a constant. And so the tangent substitution is telling us that I can substitute √3/2 a tangent theta is equal to x, or whatever is acting like our x. So this is my substitution. Let's see if it gets us anywhere. Now I also want to be sure to, replace my dx with d theta and whatever else comes with it. So let's go ahead and differentiate both sides of this substitution equation in orange. If I take the derivative of the left side with respect to theta, derivative of tan is secant squared. So I get root 3 over 2 secant squared theta d theta is equal to, if I differentiate the right side, I just get 1x dx, so just dx. So I can go ahead and sub in root 3 over 2 secant squared theta d theta in for dx. So let's go ahead and do that. Beautiful, beautiful, beautiful. And let's make the other substitutions as well. So we have that root 3 over 2 tan equals x plus 1/2. So I'm going to just put that in the parentheses over here. So we have root 3 over 2 tan theta. All right. I think we're in a good spot. So let's clean up this mess. I'm going to first pull this thing out, this constant in the front. So let's clean it up, clean it up. I'm going to put the secant squared on top because it's multiplication. We can do that, no problem. And on the bottom, I'm going to go ahead and square the root 3 over 2 tan. Now root 3 over 2 squared is just, itself multiplied twice, or multiplied by itself, whatever. Root 3 times root 3 is 3. That's root 9, right? So what we get is 3 over 4, and now you should say, Eureka, yay! Look at that. We have 3 over 4, 3 over 4. This is telling us I can pull it out, and it's a beautiful day, because we can do that. So let's go ahead and see what's going on here. So if I pull out a 3 over 4 on the bottom, I'm left with 1 plus tan squared theta, and from here you should be saying, oh my gosh, yes, I can sub in this guy. I can sub in secant squared in there. All right, these cancel. Now what do we have? We have 1 over 3 over 4, right? To simplify, keep the top times the bottom flipped. So that's just 4 over 3, what we have. That's a constant. I'm going to pull it out. Okay. So on the outside, these constants are going to simplify to 2 root 3 over 3, right? And then, so this is just going to become 2 root 3 over 3 theta once I take the integral. And remember, what we want to do is we don't want theta, we want something in terms of x. So we go to the OG substitution right here. Root 3 over 2 tan equals x plus 1/2. And we solve for theta. So the first thing I can do, I can get rid of this root 3 over 2 by multiplying both sides by that. So I get tan theta is equal to, let's see, 2 over root 3 x plus 1 over root 3. And finally, to get theta by itself, I can take the tan inverse of both sides. Beautiful. Let's put it in. So we have 2 root 3 over 3 times theta, which we just found was tan inverse of all of this stuff. Can't forget the plus c. There it is. So this is my final answer boxed. All right, so we'll do one more problem. We're going to use a triangle here again. I mean, you could use a triangle for any of these problems, but here it specifically asks us to use a triangle. So that's what we're going to do. Evaluate the indefinite integral using a trig substitution and a triangle to express the answer in terms of x. All right, so what do we have here? This looks like a sine substitution, because it looks like this guy is acting like our a squared, and this guy is sort of acting like our x, right? Okay, so let's go ahead and maybe write this in terms of, you know, what a and x are first. So let's go ahead and do this. So this is like our a, and here 16, the square root of 16 is 4. So this is actually 1 squared minus 4x squared over x squared dx. And so here a is 1, and what's acting like our x is 4x, and so our substitution is going to be 4x, so maybe I'll do it in orange to be consistent. So 4x is equal to 1 sine theta, which of course is just sine theta. So this is our substitution right here. Okay. Let's actually draw the triangle since we're here. So this could be, let's see. Well, actually, let's draw the triangle in a minute. Maybe it'll look easier once we do some more of these steps. Okay, so 4x is sine theta, so let's go ahead and sub that in. Okay, so I want to get rid of this too. I have to manipulate my substitution equation to get in terms of theta. I can square both sides to get an x squared here, so let's do that. If I do that, I get that 16x squared is equal to sine squared theta. And dividing both sides by 16, I get x squared equals sine squared over 16. Perfect. So that's going away. We don't want x's and thetas to be in the same house. All right. Now, instead of dx, remember we have to differentiate our substitution equation. So on the left, I have 4 dx is equal to cosine theta d theta. And dividing by 4, I get dx by itself, which is what I wanted. So we're going to do cosine theta over 4 d theta. Okay, so the first thing I'm going to do is, let's see. I'm going to first bring out the 1/4 from here. So if I bring out the 1/4, I get just trying to clean it up a little bit. I'll just leave that there for now. Now, 1 minus sine squared is equal to cosine squared, so I can clean that up under the radical. So I get this, and I'm making some progress, I think. All right. So the square root of cosine squared is just cosine. So that's changing there. All right, so what I'm going to do from here is I'm going to get rid of that weird denominator. So remember, what I do is I keep the top multiplied by the bottom flipped. To get rid of that weird denominator. And I'm just doing this step by step just so you guys can see what's happening here. I'm going to bring out the 16. So far I hope you guys are following this. Now I'm kind of in a rut right here because, I mean, I could change this to possibly cotan squared. You know, I could do something like that. What I'm going to choose to do though here is I want to get this in terms of all sines or all cosines. So I'm gonna turn everything in terms of sine by replacing this guy with a Pythagorean identity. Cosine squared equals 1 minus sine squared. Remember that? So that's what I'm going to do. And I'm going to erase some of this stuff so I can make room. Oh, I know the battery's low. Okay. So 16/4 is just 4, so I'm going to put that on the outside. Then I'm going to replace cosine squared with 1 minus sine squared, just so we're all, you know, in the same trig function. Now what I can do is I can separate out the denominators. So this is just, you know, the integral of 1 over sine squared minus the integral of sine squared over sine squared. And we can see here that this is just 1. So I'll replace that with 1. Okay, now I need to look at my cheat sheet because this guy is in our integration table. Now let's figure out where it is. This is... Aha! I'll write it up here. So this is coming from our integration table, these special integrals. This is 4-19, and I'm just going to write it pretty small down here. So this is 1 over sine to the m of theta d theta is equal to -1 over m minus 1 cosine theta over sine to the m minus 1 theta. Okay, plus m minus 2 over m minus 1 times the integral of 1 over sine m minus 2 theta d theta. Okay, so that's what this integral says. You know, the left side equals all of this stuff. So let's go ahead and do that. I think some things are going to actually cancel out pretty nicely. So that's cool. Let's see what happens here. So using this, it appears that m is equal to 2. So I'm just plugging in 2 anywhere I see an m in this formula. So let's do that. Let's do that right here. We have -1 over 2 minus 1 cosine over sine to the 2 minus 1 theta plus 2 minus 2 over 2 minus 1 times this weird integral 2 minus 2 theta d theta. Alright, so what's awesome is that this all cancels out to 0 because this part is 0 and it's multiplication. Lovely. Now this becomes -1 over 1 cosine theta over sine theta. Beautiful. Alright, great. So this is just negative cosine theta sine theta. Nice. Alright, let's replace that. Beautiful. This guy we know to be theta when we integrate it, so let's replace that with minus theta. And finally, I can distribute the 4 giving me -4 cosine theta over sine theta minus 4 theta. Okay, so here's where the triangle comes in because I don't want to use theta, I want to use x. So the first thing to do is to figure out what theta is, and that's by using this guy, the substitution. 4x equals sine of theta. So we have 4x equals sine of theta. Therefore, taking the inverse sine, we get theta is equal to sine inverse of 4x. Okay, so let's write that out. We have negative 4 cosine of theta, which is sine inverse of 4x let's see. Oh, sorry. Over sine of minus 4 theta. So minus 4 sine inverse of 4x. So we can clean this up a little bit. What's cool in the bottom, in the denominator, the sine and the sine inverse are, you know, inverse functions. So we just are left with 4x on the bottom. Let's write that. Okay, and let's go back to this triangle thing. So originally, this is what we had originally. Originally we had the square root of 1 minus 16, or actually let's write it like this. Well, yeah, fine. 16x squared over x squared. And so somehow we need to use these things under the radical with Pythagorean theorem and build a triangle there. Okay, so so the question is, you know, what are the legs of the triangle and what is the hypotenuse? So let's see. So if this is theta, then what we can do is we can, you know, we can figure that since this is 1 minus 16x squared, then 1 could be the hypotenuse, right? You know, if this was plus, then 1 would be a leg, but let's make 1 the hypotenuse here, and let's say that 4x is the other leg. And so what this becomes is 4x squared plus something is equal to 1 squared. And so 4x squared we know to be 16x squared. And we can take the square root. And we see that the other leg is exactly what we have in our numerator here. So this is just going to be 1 minus 16x squared. All right. So now that we have that taken care of, sine inverse of 4x well, that's just going to be theta, right? So we're looking at this piece now, sine inverse of 4x. And sine is opposite over hypotenuse. So sine inverse is just going to be theta, right? That's, you know, we kind of purposely set it up like that. And so what this is saying is, well, negative 4 times the cosine of theta. What does that equal? Right? This whole thing is just theta. So what's negative 4 cosine theta? Well, cosine theta is adjacent over hypotenuse. So this is just going to equal negative 4 root 1 minus 16x squared. All right, so these 4s can cancel if we want to simplify this a little bit more. So we're just left with our final answer being negative root 1 minus 16x squared, over x minus 4 sine inverse of 4x plus c.